So notice we've got the derivative, d over dx, of the integral from c to x of f of t dt, and c represents a constant. So this is the second fundamental theorem of calculus. Remember, the first fundamental theorem of calculus is how you actually evaluate a definite integral. So that's how we're going to work out. Let's see why this works here by using the first fundamental theorem on the inside. So we'll start on the inside and then work our way to the outside with the derivative. So there's not a specific notation for the antiderivatives in order to integrate lowercase f of t. So oftentimes what is used is the uppercase letter. So I'm going to define that first. Let's say that capital f of t is an antiderivative of lowercase f of t. So that way we have some notation, so that when we integrate lowercase f of t, we would get capital F of t. And notice this is a definite integral from c to x. And then if you want to turn this into a little bracket here, it's a little easier. And we still have the derivative here on the outside. Now, just like you would with any other definite integral, you would substitute in the upper limit x and then subtract what you get when you substitute in the lower limit c. So let's have the derivative on the outside. And now we substitute in x for t, that would be capital F of x. And then minus, substitute in c for t, so that would be capital F of c. Now we're going to take the derivative of that. So the derivative of capital F of x, well, if capital F of t is an antiderivative of lowercase f of t, that means that when you take the derivative of capital F, it gives you back lowercase f. It just happens to be x instead of t. So that's like the difference between sine t versus sine x. The same function, just a different variable inside. So the derivative of capital F of t would be lowercase, capital F of x would be lowercase f of x. Oops. Minus, well, the derivative of capital F of c, you might think it's lowercase f of c, but remember c is a constant. So if you plug some constant into a function, that just gives you some other constant. So capital F of c is just some constant, even though we don't know what it is. And remember, when you take the derivative of a constant, that's 0. So we just end up with f of x, and that's what the second fundamental theorem of calculus tells you. Another way to think about why this works here is when you have the derivative of an integral, those are reverse processes. So they should, in a sense, cancel each other out, and you just get back the function you started with. Capital F of t is identical to capital F of x, just a different letter inside. So let's see how this works on some example problems here. So find f prime of x. So define the derivative. Now this function is defined as a definite integral. So a little different there. So f prime of x would be the derivative of this definite integral from -1 to x of the square root of t cubed minus t dt. So whenever you have that derivative of an integral, you want to think, well, let's see if this fits the second fundamental theorem. Because oftentimes the actual function that's in here is either going to be very difficult or impossible to actually integrate by hand. So let's see if this fits it. We've got the derivative of an integral, the lower limit, let's see if that's a constant. It is. -1 is a constant, and the upper limit is x. So when that happens, it fits it exactly. We know this is just going to equal f of x. So the only thing that changes, the function stays identical, this square root of t cubed minus t, except the x gets substituted for the t. Because notice it was f of t and then it's just f of x. So the x just replaces the t. So this would equal the square root of x cubed minus x. This fits the second fundamental theorem exactly. So when you know the second fundamental theorem, you don't have to try to go through the whole process of integrating and then taking the derivative. We proved why it works over here, but in practice, you actually just essentially cancel those two out without having to go through this whole process. Now that we've seen why it works. All right, let's take a look at one more here. F prime of x be the derivative of this definite integral again, from x to pi over 3. This time our function is cosine t to the fifth. So we still have the derivative of an integral, but notice in this case, something's a little bit different. The lower limit is not a constant, it's x, and the upper limit is our constant instead. So remember the property of definite integrals you can use here. If you want to flip or switch the lower and upper limits, you can, as long as you just switch the sign, because that's going to change the order that they're substituted in. So, since the constant's up there, that's going to mean we have to flip it, flip the lower and upper limits, and that makes our answer negative. But again, other than that, it fits the second fundamental theorem, so the variable x just replaces the t, so it's negative cosine of x. Now you could write it this way to the fifth, but I prefer to write it with parentheses to the fifth, a little more clearly. The cosine x is what's being raised to the fifth power. So that's what f prime of x would equal, using the second fundamental theorem of patterns. All right, let's take a look at a couple more that are a little bit different. These just say simplify. And notice here we've got parentheses instead of brackets, really the same thing, doesn't really matter. We have the derivative of an integral. So here the derivative and integral symbols are already there, as opposed to the last two problems where we actually had to take the derivative. So you want to see, well, let's see if this fits the second fundamental theorem of calculus or not. Our lower limit, 0, is a constant, okay, so we don't have to flip it on this one. However, notice what's slightly different. In the second fundamental theorem, the upper limit is just x. But here, the upper limit is 2x rather than x. So, when it's just not x, when it's something other than x, that's like our function inside. That means we just have to use the chain rule. So when you're simplifying it using the chain rule, remember you just have to multiply by the derivative of the function inside. And the derivative of 2x is 2. So that's what you have to multiply by. In this case, in the normal second fundamental theorem, the x replaces the t. But here, we don't have x as our upper limit, it's 2x. So the 2x is going to replace the t. So it becomes sine of 2x cubed rather than the sine of t cubed. And then you can simplify that to be 2 times the sine. When you cube that out, 2 cubed is 8, and then x cubed gives you x cubed. So that's what this would simplify to be, using the second fundamental theorem. Again, when you recognize it, anytime you have the derivative of an integral, that's when you're using that second fundamental theorem. So do one more of these, the derivative of an integral. In this case, a couple things happen. Notice the lower limit is not a constant, it's the upper limit. It's a constant. So since the upper limit's a constant, again, this is one where we'd have to flip the lower and upper limits, and that would change the sign. So you need a negative due to that. And another thing that happens, notice it's not just x, it's x squared. So that's like our function inside. So again, whenever it's not just a single variable x, you have to use the chain rule. And using the chain rule, you have to multiply by the derivative of that function inside. And the derivative of x squared is 2x. And then, normally again, x is what replaces the t. But here, it's the x squared that's going to replace, in this case, both of those t's. So it becomes the cube root of 8 times x squared plus x squared to the 4th. And then you can just simplify that a little bit. So we have negative 2x times the cube root of 8x squared plus x to the 8th. That concludes the notes for AB Calculus on the topic of the second fundamental theorem of calculus, part 1.